Okay, let's get started. So I'm going to continue with linear algebra today, and actually I think I'll pretty much be done with linear algebra by the end of this week. So we'll start with signal systems and transforms next week. So today I'm going to focus, today and actually most of this week will be focusing on eigenvalues and eigenvectors. And the last class actually been stochastic matrices, but this lecture and next lecture will be on eigenvalues. How many of you have seen eigenvalues before? Could you raise your hand? Okay. All right, so pretty much everybody has seen it. So this would be sort of, I guess, revision for you. One thing that I find is that many people understand how to compute eigenvalues, but they don't necessarily have a good intuition for it. What does it mean, or why is it important? So let me re-ask that question. How many of you think you understand why eigenvalues are important? Or, I mean, really get it, you know, like if you look at a matrix, you can say, yeah, these must be the eigenvalues, and this is why it's important. How many of you? Okay. So, unfortunately, this is what happens when you do eigenvalues in undergrad class. You have the mechanics of it. You kind of, somebody can give it to you, you can go through the computation and come up with it. But you don't necessarily have any idea what it means or why it's important and why people make such a big deal out of it. So hopefully by the end of today's class, you should have a much better understanding of both how to compute eigenvalues and why they're important. And when you do control theory, you will see very clearly what happens with eigenvalues. Okay, but the first step is to understand what's meant by a linear transformation, okay? And a linear transformation is essentially a way of taking a vector and transforming it into another vector, okay? So we take some vector, let me just write it out. I'm going to do the example from here. So let's say we just have a vector with two elements, it's A and B, just keep it simple. And what's going to happen is that we're going to compute from this a new vector, which is 2a plus 3b and 6a plus 2b. So this is a vector, this is another vector, but what's happened is that in this vector the first element has gotten a weighted sum of these two pieces, okay? If you recall what when we talked about the linear dependency was, you see that this is just a linear dependency of 2a plus 3b is linearly dependent on a plus b. So if you think of a and b as being some basis or some set, 2a plus 3b is just a weighted sum, 2 times a plus 3 times b. So take 2 times the first one and 3 times the second one. If you want to make it more interesting, you know, just make these weights add up to 1. So you could have, you know, 0.2 and 0.8, for example. Then you're getting some kind of mixture of a and b. Okay, that becomes this element, and this element is again a mixture of these two. So if you go back to the example I had, you know, with the Mongolian grill, right? If you go to Mongolian grill and you have over here, you know, some tofu and some spinach, you know, this gives you the menu, the recipe for making for the first customer. This is the recipe of the second customer. Okay, it's a linear combination of these two elements. So in some sense, what we're doing is that we're taking a representation of the basis of you know, which are the individual elements, and we're applying to it something which allows us to compute what this combination are. It turns out that this is it's just a matrix. This matrix over here, 2, 3, 6, 2, is the trick, if you will, or is the recipe that tells us how to go from here to here. So you can just put this as equal to now, because what we're doing is we're taking this matrix and applying it to this vector over here. So any matrix, any square matrix anyway, can be viewed as a transformation. Okay, and that is the secret to the whole thing. Okay, if you understand that, you'll understand sort of what eigenvalues and everything are all about. So what we're trying to do is, we have some vector, and through some physical process, we know that it becomes some other vector. Okay, and the trick is that we are representing the transformation in the form of a matrix. Okay, once you do this, then you get this transformation right here. Okay, so matrix multiplication becomes really a way of applying this transformation onto this vector over here. Now the interesting part is that the effect of this matrix on this vector, it doesn't really depend on this vector at all. It could be AB or CD or whatever. The matrix is what's important. Okay, as long as you can use this as an operator, as a transformation, you can apply it to anything that you want. And so the properties are related to this. This is where we focus our attention on. This just happens to be the vector that we're working with to get this transformation over here. Okay, we could put CD or any number over here, you would still get the same transformation. Okay, so what we're trying to do now is we started out with the matrix as being just this bunch of numbers. You know, you have a bunch of counts of TCP and UDP and things like that. And now we're kind of moving further along. We're actually attaching some semantics to the matrix. We're saying that this matrix is going to have this property of being viewed as a transformation. Okay. So are there any questions about this over here? Okay. So just to give you a sense of this, that's why I had those two homework questions. So the first homework question was saying, what was it saying? Okay. So how do you get from ABC to the vector, I think 3A plus 2B plus 9C, or something like that. So if you use this matrix, 3, 0, 0, 0, 2, 0, 0, 0, 9, sorry, it's not plus. 3A, 2B, 9C. We see that we get the effect that we want. Okay, and we need zeros here because the first one is being multiplied by a scalar value, the second is multiplied by a scalar value, third one is multiplied by a scalar value, and in fact all the others are not being. So this matrix here is scaling up each of these components by a scalar value, and there's no mixing at all, right? And so that's why this can be viewed as a transformation matrix. Think of some kind of balloon, and in x dimension it expands by 3, by y dimension expands by 2, and z dimension expands by 9. So that's what the scaling is doing. It's pushing it in different directions by different values. Okay, so this is the operator over here. So I hope most of you got this right. You must have exchanged your whatever, your cards and so on. Okay, so any questions about that? So that's just to give you a sense of the transformation and for the general case, we need to just have the AI over here, AK, and it will be AN, and that's going to give you the same effect. It'll be or whatever. So that's going to give or maybe just I call it X1 to Xn, and it gives you the same effect of the scaling from A1, X1, AN, Xn. So that's the same kind of thing that's going on over here. And again, that's the solution to the second homework problem. So as you can see, what's happening is that we are now mentally kind of going on to choosing the matrix in a way so as to achieve a particular kind of output. Okay, we're choosing this to do the right kind of scaling. Okay, and that's again the mental process I wanted you to go through for this. Okay, any questions about that? Okay, so the next thing I want to talk about is this notion of composition, and I want to do an example of that composition. So we let's just say that we have some matrix A applied to vector x gives you some vector x prime, okay, and some vector B applied to x prime gives you the vector x double prime, okay, and so we recognize A and B as being transformations. So the question is, what do we have to do to go from x to x double prime? Okay. And I mentioned to you in the first class about the, or maybe second class, about the notion of multiplication. Why do we choose multiplication? And the reason is because the way we go from x to x double prime is that we are applying b to ax, okay? And so if you're going to apply, if you say this is given by the matrix C, then we find that C equals BA. And of course, in that order, it's not AB, but it's BA. So what we're doing is that the matrix product of two transformations results in a matrix, okay, which gives us the effect of those two transformations. So we now have the ability to think of what we can think of as algebra for transformations. Yeah. Okay. So people are coming in late. Okay. Look, you're disrupting everybody, disrupting me, most importantly. Okay? Don't do it. Okay? You can leave a few minutes early and get here on time. If I can get here on time and everybody else can get here on time, so can you. Okay? So from now on, all of you coming in late, just don't do it. The class starts on time. I said that in the first class, which you missed. Okay? So don't do it. It distracts me. It puts me off my schedule. And it's not good. Okay. All right. So the whole purpose of defining matrix multiplication in the way that we defined it, which is not the obvious way, because addition was the obvious way. We just add row by row, element by element. But for multiplication, we did something funny, and that's because of the fact that when you define it that way, we get a very nice algebra for transformations. You can take any transformation, any other transformation, and you get this product, and that gives us the combined transformation. To show this, let's just try it out. So we've already seen this over here. We've seen that this matrix over here, 2, 3, 6, 2, is going to give us this transformation of 2a plus 3b, 6a plus 2b. Okay. Now let's take this matrix. This vector, 2a plus 3b, 6a plus 2b, and I'm going to apply to it the transformation, which is a very simple transformation, 2, 0, 0, 2. And from your homework, you'll realize that what this is going to do is to multiply each element by 2. It's a scaling by 2 in both dimensions. So this is going to give us, just by inspection, 4a plus 6b, 12a plus 4b. Right? That's just because that's the scaling. That's the that's the homework assignment. How do you do the so that's a diagonal with the a1 equals a11 equals 2 and a22 equals 2. So that gives us what we want. So the question is, can we get this final result over here more easily? And the answer is yes, because we can use this rule, C equals BA. So what we're going to do is, let's just use this over here. So I'm going to take this matrix 2, 0, 0, 2 and apply it to this one over here, because that's what I said. This is B and this is A, and that should be equal to C, and this one is going to be 2, which is it? I can't read from here. So 2 times 0 is 4, sorry, it will be 4, 6, 12, 4. And if we apply 4, 6, 12, 4 to the vector AB, that should match what's in the circle, 4a plus 6b, 12a plus 4b, right? So just to repeat, this was the vector matrix A we started out with. Let's call that transformation T1, and this is the second transformation T2. And the combined transformation, let's just call that T, is given by the matrix product of T2 and T1, and then the effect of applying C on the vector AB is the same as applying the two transformations one after the other, because this was the first transformation, this is the second transformation, we got this, so it works out to be the same. And in general, you can prove it for any transformation of anything. It's just a very simple exercise to show that, and it just follows from the definition of matrix multiplication. Okay? So any questions about that? Okay, you're really late, but you can go get that seat over there, and don't do it again. Okay. I mean, this is ridiculous. This is 15 minutes late. Okay. Any questions? So the main point is to understand that first, matrix is transformation, and second, transformation can be composed. Okay, so we can actually think about these transformations like this, and say that T1 composed with which is some composition is going to give you a transformation. Yes.
So in one lecture you mentioned matrix multiplication is not commutative.
Commutative, correct.
So for example, if they do have like same dimension, they are commutative?
They're not, they still won't be commutative. So T1 times T2 in general won't be the same as T2 times T1, okay, even if they have the same dimension.
Suppose they are both square matrices and they are both transformation.
If they're both square, no, because again, it's even if you think of it from the perspective of transformations, it's not necessarily the case that the transformations are going to commute. Okay, you can actually just write out the terms, and you'll find that they don't have to be the same. Okay, there are some conditions under which they'll be the same probably, but I think if they're both diagonally, probably commute. But I'm not sure of it. Okay, but in general, no. In general, transformations do not commute. So it is important that it's BA and not AB. Okay, if you do AB, you get something else. Okay. All right. So I want to now focus on a specific kind of transformation, and then we'll take a break. Okay. So I want to focus on this transformation over here. So this is the vector I'm going to look at, AB, and I'm going to focus on this very simple one, 2, 0, 0, 2, and which gives us the vector 2A, 2B. Okay. So what do we have here? We have some vector AB, and we're multiplying it with this, or pre-multiplying with this particular transformation A, or I'll call it T1 just to keep it as a transformation. And what's happening is that we can write the right-hand side where it looks like this, 2 times AB. Because if you remember, when you multiply a vector, a matrix by scalar, the scalar multiplies each element. So the scalar 2 multiplying AB is going to give us the matrix 2A, 2B. Okay, that's what's going on. So what we have here is this interesting phenomenon, which is that this one over here, which is a complicated operation, which is a matrix multiplication, can be replaced by a simple operation, which is a scalar multiplication. Okay, just think of it from a perspective of computer scientists. Okay, somebody is saying, I have this vector, let's say it has 1,000,000 elements in it, and I have this matrix, which is 1,000,000 times 1,000,000, right? It's a lot of work to compute. Each element is going to be 1,000,000 products and 1,000,000 ads. Okay, so, or one less than 1,000,000 ads to be precise, 999,999 additions and 1,000,000 multiplications, order of 1,000,000, right? But I can replace all of that with just 1,000,000 multiplications, no additions, and the multiplication by the same scalar, which is much easier. Okay, so there's a dramatic simplification in the computation complexity, and so we kind of wonder, when can we do this? Under what circumstances does it become possible for us to take a transformation on a vector and replace it just by scalar multiple? Okay, and the answer is that we can't do it all the time. We can't do it for everything. Okay, we can do it only for certain vectors. Okay? For a general matrix, you can only do it for certain vectors, and then for those vectors, these multiples over here turn out to be certain multiples. Okay, and so these are called the eigenvectors and eigenvalues. So this multiple over here is called the eigenvalue, and this vector for which it works is called the eigenvector. Now, in this particular case, we have a fairly straightforward transformation. We have a doubling transformation, okay, which is trivial. Okay, it's chosen to be trivial. So just by inspection, it becomes clear that this is going to work for essentially all vectors AB. Okay, so the set of eigenvectors for which it's going to work is basically all vectors. All vectors are going to be okay for this particular transformation, and the eigenvalue is going to be 2 because that's what it is, right? That's what you get over here. So we get this very simple thing. But what if I told you the vector matrix was not 2 0 0 2 but was 2 0 0 3, right? Now what's going to happen is that we have this over here. You have 2a 3b. So we can't put 2 over here. That's not going to work. It's not going to work. So what can we do? Okay, anybody have a suggestion? How do you get this to, how do you get an eigenvalue out of this? How do you get a scalar multiple out of this?
Compute.
Compute. No, I want to do it by inspection. I don't want to compute it. It's too much work. Yeah.
For example, there's a relationship between A and B.
What relationship between A and B will give it to you?
B is like 2/3 of A.
B is 2/3 of A. Yeah, that's one way of doing it. There's a very simple way of giving an eigenvector and an eigenvalue for this. Very simple. Yeah.
So if you multiply the matrix by the vector A0, it's just going to give you.
That's right. So let's say we zap this out. We make this a 0. Okay. Then this is going to become a 0 over here because that's a 0 from there. And then we can say that this is basically 2 times A0. Remember, I'm not saying it's going to be true for all vectors. It was the case that when it was 2, 3 or 2, 2, it was for all vectors. But in this, for this matrix, I don't have that. I'm going to choose a particular vector, the eigenvector A0, or for that matter, yeah, which is going to be anything that has a 0 here actually, which means it will be 1, 0 in general, but A0. Then no matter what I have here, I'm going to get the 2A0 over here, and then I'm going to get over here this one over here. So this, as you can see, this works. So the multiplication of this matrix on this particular vector A0 is going to give me a scalar multiple of 2, 0. Okay? And the other multiple just is going to be 0b, which is going to give me the value 3 times 0b. So it's very important to realize that the eigenvalue, this multiple over here, is not general. It's only for a particular eigenvector. So these things go hand in hand. If I tell you the eigenvalue, I'm going to tell you the eigenvectors that go with it. Okay, and the eigenvectors can be infinite, right? Because 0b is an infinite set, an infinite family of eigenvectors, but I'm going to have these hand in hand. So I can't just say here are the eigenvalues, here are the eigenvectors. They're not separate. You got to compute one, and the eigenvectors go with it. Okay, and that's why I wanted to show you this over here, because you can see right away that with this matrix you don't have this nice property that all vectors. No, it's got to be just this. It's also an infinite family, but it's going to be like, okay, so let's do the homework problem for the eigenvalues, because the easiest way to understand eigenvalues is to work with that example over here. So I talked about how to compute the eigenvalues for a very simple transformation, which was the scaling transformation of by 2, which was 2 0 0 2, and then the other one. Okay, so let's look at the transformation for this matrix. Compute the eigenvalues for this matrix 1 9 4 1, which was the homework problem. And the way to compute it is to essentially solve it, right? So if we do it like this, we know that. So let me first define what the eigenvalue is. Maybe I should do that. So we have matrix A. That's our matrix. And that's viewed as a transformation. And it's a square matrix, n by n. It's a square matrix. Okay. And we're going to apply it to a vector x. And that's a vector, which is n vector. Okay. And what we're saying is that the product of the matrix on the vector, or the transformation of the this transform for some x, is equal to a scalar multiple lambda x. Lambda is a scalar. And this one is the same vector again. It's a vector. It's an n vector. Okay. So what we're saying is this complicated operation of a matrix applying on a vector can be replaced by just a scalar multiple. That's what we saw earlier. And we'd say for those vectors x, we call x the eigenvector, and the lambda is the eigenvalue. That's the formal definition of eigenvalue and eigenvector. So eigen, I believe, means right. Is it correct in German? Is that right? Proper? Something like that. So that's the meaning. So how do you compute the eigenvalues and corresponding eigenvectors for this matrix over here? We'll just write it out. We know that for some x, this vector, let's just say the vector is x1, x2. So this A times x should be equal to lambda times x1, x2. This is by definition. Okay, that's the definition right there. So we can write this like this. We just expand this out. We get this equation x1 plus 9x2 equals lambda x1, and 4x1 plus x2 equals lambda x2. This is just by expanding the matrix. And we should take lambda to the other side. We get this equation just over here. I'll just write this down. 1 minus lambda x1 plus 9x2 equals 0, and 4x1 plus 1 minus lambda x2 equals 0. Okay? So that's just, again, simple math. And so now what I can do is I can write this in a matrix form again. And the way I do it is to just simply write this in the form like this. I just say, here's a matrix, 1 minus lambda, and you get 1 minus lambda again, and 9, 4, okay, times x1, x2 equals the 0 vector, 0, 0. And again, just to keep things, I call this A, this x equals 0, okay? I haven't done anything complicated here. All I've done is to simply expand out the definition of eigenvector, eigenvalue, and eigenvector to come up with this system of equations. And we recognize that the right-hand side is 0, so we call this a homogeneous system of equations. That's just the name for it. Let's see if we can apply Kramer's rule to it. So let me just go back and remind you what Kramer's rule is. Kramer's rule says that xi, the ith value, okay, corresponding to this this one over here, this ith value of the eigenvector is given by d sub I over d, where d is the determinant of the matrix A, okay, and d sub I is the matrix A, is the determinant of matrix A, and the ith column replaced by B, by the right hand side B. That's the determinant. Okay, that's the definition of Kramer's rule. Now the interesting part here is that B over here is 0. Since B is 0, the ith column is being replaced by 0. If the ith part is being replaced by 0, we can always expand by the ith column, right? And which means that we're going to get a determinant value of 0. So if you remember the determinant lecture, what we do is the value of the determinant is the Aij value multiplied by the cofactor. It doesn't matter what the cofactor is. The Aij value is going to be 0 for that column. And so all of the di's are going to be 0. So this is all going to be 0. What about the determinant of the matrix itself? Well, we don't know, right? But we know that all the xi's are going to be 0 for sure, right? Unless, there's an unless over here. It'll be 0 for sure because all the di's are 0, unless d itself has a value of 0. If it is 0, then the x sub i's are going to be 0 over 0, which is unknown. 0 over 0 is undefined, right? So we have the following situation. Either the determinant D has a value which is non-zero, in which case all the xi's are definitely going to be 0, right? And so we have this trivial solution that a times x is lambda x, where lambda is 0 and x is 0, right? So we haven't got any information out of it. It's kind of uninteresting. You're saying ax is lambda x, yeah, sure. The eigenvector is 0, the eigenvalue is 0, and it's a trivial solution. You know, we didn't learn anything from it. It was no fun, right? On the other hand, if D is equal to 0, then x sub I from Kramer's rule is 0 over 0. Then we don't know, right? Maybe x sub I has got some interesting values. You know, let's go find out, right? So the important thing here is that for this to work, for this to happen, we need to have the matrix, this matrix over here, A, to have a 0 determinant, okay, which is what's going to make our life interesting, okay. So this step is critical, okay. So I want to make sure everybody understands that. So are there any questions about this so far? Okay. So I'm just applying straightforward application of the principle that if you have a linear system of equations, which is what we did last time, ax equals b, then Kramer's rule tells us that x sub I is given by di by d, and the d sub I by definition is the matrix, the determinant of the matrix A, where the ith column is replaced by b. It's homogeneous, so b is 0, so d sub I is all 0, so x sub i's are all 0, right? Unless the determinant d is also 0. Okay, that's the chain of logic, and it's a, you know, obvious and straightforward chain of logic. You can't get around it. Okay, but the consequences are huge. Okay, which is why I'm kind of pushing this point here. So are there any questions about this? So what we're going to do here now is to look at the system. I'm just going to erase this for now to give me some space, and say that this matrix has a determinant of 0. So I'll take this and replace this with this vertical value here, and say this determinant is equal to 0. That's what I said, right? Again, why is this 0? So that we have interesting values of the eigenvector x sub s. Okay, so what does this give us? We can expand this. Okay, if you remember, for a determinant of the thing a, b, c, d, it was equal to ad minus bc. That was the definition of a 2 by 2 determinant. So if you do this, we're going to end up with this determinant, basically 1 minus lambda square minus 36 equals is the determinant. Okay, and this is equal to 0. Because we said that determinant A equals 0. This implies 1 minus lambda square minus 36 equals 0. And I chose these numbers, you know, carefully so that I don't have to do much work. And so we get 1 minus lambda square. 1 minus lambda square equals 36. So 1 minus lambda equals plus minus 6. And so lambda equals either 5, what did I do? Okay, let me do this, minus 5 or 7, okay? So there are two values of lambda that I got out of here, okay? So what does this mean? It means that there is some vector here, which we haven't figured out yet, but we will in a minute, such that when this matrix multiplies that vector, it's as if it were multiplying by the value minus 5, and there's some other vector here, so that if you multiply a by that, it's like multiplying by the value 7. Okay, it's kind of funny. I've told you what the multiples are, but I haven't told you what the vectors are. Okay, and that's just the way it works out. Okay, it works out that you find out the eigenvalues first before you find out the eigenvector, though it's logically speaking, we don't want to think about it that way. We want to say, here's a matrix, and if you multiply this vector, it's like multiplying by minus 5. And if you multiply the other vector, it's like multiplying by 7. But we don't do it that way. The computation actually works backwards. Okay, and that's confusing. At least I found it confusing. When I was studying eigenvalues and eigenvectors, I'd say, yeah, okay, great, I got the eigenvalues, fantastic. So I'm done, right? No, I'm not done. Because all I've told you is that there is this unknown vector which is going to be scaled up as if it's a linear scaling by 5 or minus 5 or 7. Okay. Any questions about this so far?